Hi, my name is Michaeli, and I'll present Alias-Free ViT, fractional shift invariance via linear attention, a joint work with Daniel Sudri. Shift invariance is a fundamental prior for image classification. It's reasonable to assume that a small translation of an image does not change its class. This idea motivated the design of early convolutional models. Transformers, however, were initially designed for sequential tasks and are therefore quite sensitive to image translations. Although convolutional networks are less sensitive, they are not perfectly shift invariant due to aliasing and downsampling in nonlinearities that break convolutional shift equivariance. This problem is addressed by alias-free models that use low-pass filtering and upsampling layers to prevent aliasing. Our goal is to use the same principles to construct a shift-invariant vision transformer. Our main contributions are as follows. First, we identify a class of shift-equivariant attention layers that include linear attention and cross-covariance attention. We then design an alias-free vision transformer that uses this contention mechanism and alias-free components. We show that this model is 99% consistent under fractional cyclic shifts and significantly more robust than other baselines to realistic shifts, while maintaining a comparative accuracy. We start with a quick overview of a vision transformer. We begin with an image that we want to represent as a sequence of tokens to feed into a transformer. We split the image into patches and linearly project each patch with the linear layer. We usually add a positional encoding to each token, and then propagate the sequence into a transformer encoder, which is a stack of attention blocks. For classification, we typically add a special class token to capture a global representation, which is used as input to a classification head. Next, we describe how we build a shift-invariant vision transformer. The first part to handle is the patch embedding. An interesting observation is that the patch embedding stage is equivalent to a striated convolution. This is not shift-equivariant because aliasing is introduced by the implicit downsampling in the striated convolution, and due to the positional encoding as well. Our solution is to replace the stage with an alias-free convolutional patch embedding. We also show empirically that when we do this, positional encoding is unnecessary. Next comes the transformer encoder, where we specifically need to handle the self-attention mechanism. Its input is a sequence of patch embeddings. For each patch, we compute 3 linear transformations, giving sequences of queries, keys, and values. We then multiply the queries and keys to obtain an attention map, and apply a row-wise softmax, then multiply by the values. Having the sequence representation in mind, when the input is translated, the queries, keys, and values translate in the same way, and these translations appear along the diagonal of the attention map. Therefore, applying the row-wise softmax breaks shift equivariance. To solve this, we introduce an alternative class of shift-equivariant attention mechanisms. As before, we have the query, key, and value sequences we formally show are shift-equivariant. We then multiply the keys and values to obtain a channel-to-channel matrix, which we show with shift-invariant, which means a translation of the input has no effect on this quantity. We then multiply by the queries, which obtain an overall shift-equivariant output. In practice, we integrate our methodology into EXIT, which is a hybrid vision transformer architecture. EXIT uses convolutional patch embedding, which we replace with an alias-free convolutional patch embedding. EXIT is composed of cross-covariance blocks that already use shift-equivariant attention. These blocks also use layer norm and GLU, which we replace with alias-free normalization and reduced aliasing GLU, similar to previous alias-free convnet works. Note that unlike the alias-free convnet, we do not replace GLU with a polynomial activation. Therefore, our model is not provably shift-invariant, yet it remains roughly 99% consistent under translations. We also replace the class attention with shift-invariant global aggregation. In the paper, we discuss 2 options, global average pooling and shift-invariant class attention. We evaluate our method on EXIT nano and EXIT small. In both cases, we obtain similar accuracy to the baseline and near-perfect shift consistency for both integer and half-pixel translations. We also compare to APS, a method that certifies integer shift consistency. As shown, it is much less robust to fractional shifts than our method. Considering more realistic translations, we evaluate crop shifts that mimic camera translations and bilinear interpolation fractional shifts that mimic realistic sub-pixel translations. In both cases, our model is much more robust than the baseline, the APS, and other baselines as well. To summarize, vision transformers are very sensitive to image translations compared to convnets. We use alias-free framework to build a shift-equivariant transformer yielding a shift-invariant image classifier. Our methodology combines shift-equivariant attention with alias-free components, including filter activation and alias-free normalization layer. As a result, we achieve near-perfect consistency under fractional cyclic shifts and show strong robustness to realistic translations while maintaining comparative accuracy. Thanks for listening.